right, good afternoon, everyone. This is a discussion between astronomers about what astronomy can do for you, and in particular for Earth observations. My name is Alan Duffy. I'm an astronomer from Swinburne University, and it's my distinct pleasure to be guiding our panel of some of the best and brightest in Australian astronomy to discuss this topic. Before we begin, I want to pay my respects to the traditional owners of the land upon which we meet, the Garnet people. I want to pay my respects to their elders, both past and present, and I'd like to extend my respects to any Aboriginal and Torres Strait Islander peoples with us here today. I want to thank the government, the Australian government, the Square Kilometre Array Office for putting on this event. It's not often that you get such a diverse array of very senior astronomers in a room together. And I really want you all to take advantage of this opportunity today to ask them the questions that will perhaps come to mind through this discussion, because we're going to be exploring the breadth of Australian astronomy. We're going to be discussing how it supports the exploration of space, both near and far, ultimately to the betterment of life here on Earth. So the order of proceedings is I'm going to take each of our panelists in turn with a question, and then I'll throw it open to the floor. So please get thinking, get your hands up when it comes time, and we've got some roving mics, and we'll get you involved in this conversation. So I'd like to start at the far end with Professor Matthew Bales. He's director of the ARC Centre of Excellence for Gravitational Wave Discovery at Swinburne University. Matthew, your research on gravitational waves, as well as your efforts upgrading the Malungolo radio telescope to hunt for super dense neutron stars, required rapid, efficient searches through enormous data sets. And I particularly want to focus on that initial point. How do you see this era of big data astronomy helping the satellites and future robotic explorers when they're being asked to do so much heavy computational lifting with with essentially limited power supplies as they're deep in space?
Yeah, so in astronomy, we face a massive data challenge. We're actually much good at generating data than we are at reducing it. And I think if you look at the recent history of astronomy, the most successful projects are the ones that actually put the time and effort into their software pipelines and computational infrastructure. And so I was very pleased to see the Australian government invest in the Pawsey Centre over in Western Australia. It's an $80 million facility with amazing supercomputers. But all around Australia, we've got new supercomputers coming online. At the ANU, we have the NCI machine. Our own Centre of Excellence, Osgrav, is getting a new supercomputer. It can do 3 petaflops, which is 3 by 10 to the 15 operations a second. These are amazing devices. And I think one of the things that we've learned is that efficiency of calculation is everything. So getting the right algorithms, and that reduces your power consumption. These things are not very greenhouse gas friendly. And I think that algorithmic development and optimization can really help space exploration when they've got a very limited power budget.
All right, so now we have Dr. Sarah Pearce, Deputy Director of the CSIRO Astronomy and Space Science, and is leading the CSIRO's efforts on the Square Kilometre Array. So CSIRO owns and operates a huge range of facilities for research. However, I'd like you to perhaps share the ways in which Australian-based telescopes have been used to support missions closer to home, or at least closer than the distant radio galaxies that you find, for example, as the downlink of NASA's Solar System Explorers.
Thanks, Alan. Yeah, I mean, many people in the audience will know that the role that Parkes played in the Apollo 11 landing on the moon. Hopefully, a number of you have seen the film The Dish, which is, at least broadly accurate. But Parkes has been involved with NASA and ESA for downlink for their missions since the very beginning, really, of solar system exploration. So starting with the 1962 Mariner flyby of Venus, and then most recently all the way through to the 2012 landing of the Curiosity rover on Mars, and that, I think, amazing, was it 7 seconds of terror as we watched the rover fall to Mars. But in between, Parkes has supported the Voyager 2 probe as it went past Uranus and past Neptune. And And it's also, we've also supported several of ESA's massively exciting missions, like Giotto's flyby past Halley's Comet in 1986 and the Huygens landing on Titan in 2005. So although obviously we also host the Deep Space Network Centre at Tidbinbilla, our astronomy telescopes, and in particular Parkes, have played a really significant role in space and solar system exploration over the last 50 years.
Okay. So just with a show of hands, who has actually seen the dish? Yeah, okay, I could have guessed that. All right, very good. And you've all heard of the square kilometre array as well, yeah? Ooh, okay, Jerry, got a bit more to do there. From the Square Kilometre Array to another next generation facility, the Giant Magellan Telescope, we'll have Professor Chris Tinney, who leads exoplanetary research, exoplanetary science research at the UNSW. So Chris, Australia is involved in these truly extraordinary next generation facilities, and you've been involved in the GMT in particular over many years. I wonder if you could share with us how these enormous telescopes can help us to explore distant worlds and what they can in turn tell us about our own place.
So just to give you an idea of the scale of these projects, you've probably heard a lot about the Square Kilometre Array. The other big mega project Australia's involved in is the Giant Magellan Telescope. It's the sort of blue-coloured one up in the top corner of that picture there. And to give you an idea of the scale, that building it sits in is 22 stories high, equivalent to, it's about 63 metres off the ground. It weighs kilotons and has to be able to spin around. This is a $1 billion, enormously large project, but that's what you need if you're going to try and understand the structures of planetary systems outside our own. One of the things that we've learnt over the last 2 decades is that our own solar system is not exactly normal. We have not found any other planetary systems that look like our own. And that then tells us, well, it tells us we don't understand how planets form. We don't even really understand why in our own solar system Venus and the Earth and Mars are actually all relatively similar planets. They're all in quite similar orbits. But Venus is a hellhole because it's too hot, has a very thick atmosphere. Mars is an ice ball with essentially no atmosphere. Earth, we regard it as being a nice and habitable in-between. We don't really understand why they are like that. And we need to look at more than one example if we're going to try and unravel just how common habitable environments are out there in the universe.
Fantastic. So now from next generation facilities to the current precursor, I guess, facility for the SKA, we have Professor Stephen Tingay, who's Executive Director of the current Institute of Radio Astronomy and former Director of the Murchison Wide Field Array. This is a gigantic low-frequency radio telescope in WA, the ultimate site of the SKA, or at least the Australian component. And thanks to the size, but also the technological sophistication of the MWA in particular, you've been able to play a key role in the near-Earth environment. I wonder if you could say a little bit of, to my mind, surprising ways, actually, radio telescopes have helped everything from space debris to the ionosphere.
Sure, thanks, Alan. Yeah, so one of the significant projects that I've worked on over the last decade is the Murchison Wide Field Array, which is to the bottom right of screen over here. It's a very interesting radio telescope. It's not based on a dish technology. It's based on very simple antennas that are stationary on the ground, and the telescope is fully electronically steerable. These telescopes are incredibly cheap to build, easy to deploy, almost infinitely flexible in what they can observe and the signal processing that they can achieve. Just above the picture of the telescope is a full sky image of the universe at radio wavelengths. And I'm very proud to say that the MWA is the only fully functional precursor telescope for the Square Kilometre Array, which is, of course, featured in the middle of screen. So the MWA technology is informing what we're going to build in a 100 times bigger instrument in the SKA. So our prime goal is astrophysics, making images like this, but because of the almost infinitely flexible nature of the technology, we can do many other things. And most of these things relate to what I call monitoring of the near-Earth space weather environment. So we can use the MWA as an element of a passive radar system that detects, monitors, and characterises space debris. So we can do this over an enormous field of view on the sky. We can track dozens of pieces of space debris simultaneously. We can then do orbit reconstruction. We can react to rapid breakup events, very important things when you're protecting multi-billion-dollar space assets. We can also use the MWA to monitor in real time and over almost all the sky ionospheric conditions that affect high-frequency radio communications, for example, both civil and defence applications. And we can also monitor the sun for massive coronal mass ejections that have the potential to disrupt expensive assets, not only in space, but on the surface of the Earth. So this is a really good example of the crossover technology between astronomy and space sciences. And we think there's a big role for this in the SKA.
So I hope some of you are now beginning to get some ideas, some questions. Ready yourselves, we're almost there. Our next panelist is Professor Lisa Cooley. She's Director of the ARC Centre of Excellence for All-Sky Astrophysics, otherwise known as Astro3D, from the Australian National University. Now, Lisa is Director of a national centre focused on multi-wavelength observation and making use of data sets. In fact, we have an example behind us. It feels like there's a very natural synergy between the work you and your researchers will do and hyperspectral observations of Earth. So could you talk a little bit about ways in which Astro3D might be able to help?
Yes, well, in astronomy, we're really at the cutting edge of technology. We're trying to understand how we got here and our place in the universe. And to do that, the technology is developed for the astronomy applications to view the most distant galaxies or to view the gas that's spiraling around black holes. But that technology is then transferred into many different areas that we wouldn't necessarily think about when we first start developing the instrument for technology. For astronomy. So I'm going to give you 3 examples. First example is in Astro3D we use technology called laser-guided adaptive optics. And what this is we shoot laser up into the atmosphere and we use the distortion of the laser to correct our astronomy images for the effects from the atmosphere. So it makes a very blurry image into a very sharp, clear image. And this allows us to see very, very distant galaxies that we'd have no hope of observing otherwise. Well, this technology has been converted into uses on Earth. For example, it's now used in greenhouse gas monitors continuously on Earth, and it's also been used in to detect agriculture runoff into the Great Barrier Reef that's affecting the Barrier Reef at the moment. So that's a remote sensing application of laser-guided adaptive optics systems. We also use these hexagonal fibre optics bundles, so they're hexagon shapes of fibres all joined together, and this allows us to create data cubes of galaxies. And this technology has been used in several different applications. My favourite application at the moment being used is they're currently being used to look on farms by Horticulture Australia to detect bacteria on crops, and actually installed in robots which are then running over the crops along each of the different crop rows, and then they're used to look for things like salmonella.
Wow, I had no idea about that last one. That's awesome. All right. So this is a little flavor of the breadth of Australian astronomy, everything from multi-wavelength, scanning for space debris, next generation facilities, billions of dollars, making these things work and operate, taking the data from NASA and indeed ESA facilities, and of course big data and trying to sort through enormous petabytes of information for these very faint whispers from space, which might be familiar to anyone who's tried to get a signal from a CubeSat recently in a messy RFI environment. Have any of you got opening questions? If you have, please raise your hand and we'll get 2 of our roving mics. One right in the middle. Keep your hand up if you had it.
Hi, how do you like the new Australian Space Agency to interact with CSIRO and academia?
Great question. I think, honestly, all of you can speak to this.
Closely. So I think this is an amazing opportunity for Australia to go down this path. I think this is the best chance we have to go down the path of a national agency that collects up many, many aspects of capability across the country. And I think that astronomy, while not exactly on that sort of typical space agency path, has so much to offer in terms of the crossover of technologies, big data, RF systems, tracking facilities, that the connection has always been pretty intimate in Australia between these different areas. And I think with additional coordination, with additional researchers, additional resources, and a really national approach, that we have the chance to build something bigger than the sum of the elements that we have here in this country. And I think that's really genuinely exciting. I will stress that it has to be a national level effort though.
Several of the universities are already involved in developing CubeSats, some of which are already up in space and others are being proposed at the moment. Some of them are for astronomy applications looking up in space, but there are also astronomers proposing to use CubeSats to look down on Earth for various Earth applications, such as looking at the different chemicals that there might be existing around lakes, for example.
I think from the point of view of astronomers, it's an exciting new initiative because it means that for the first time in a very long time, we can potentially actually engage with major astronomical satellites in a partnership mode. So on the figure up above there, you can see images of the James Webb Space Telescope, JWST, and the Transiting Exoplanet Survey satellite TESS. These are major missions which are going to be finding, in my case, planets around other stars from TESS, JWST, looking at planets around other stars, and in which Australia has not been able to engage in a partnership way to help set the agenda for those missions. So a space agency for Australia would potentially put us in the position to be able to engage with future missions as a partner, not just as, well, can we apply for some time on it now that you've built it?
I think the other thing we need is sort of certainty of funding for any space agency and longevity. I think a lot of Australian efforts in space have come and gone, but we need sort of bipartisan support, realistic budgets, and that can provide careers for people who might want to move in there. You're not going to get good people to come in for something that lasts for 3 years and has no money.
So CSIRO obviously does a lot of activity that is in the sphere that the space agency will have interest in. So not only our astronomy work, but enormous amounts of work in Earth observation, in advanced manufacturing. So we're very much looking forward to the space agency and very supportive of the government's announcement, and working very closely with the expert reference panel over the next 6 months, I guess, as they develop plans and decide what kind of space agency it is we're going to have.
All right, we have a question down here at the front. And then can I see, is there any more hands? Feel free. Okay, and we have a second microphone. If we could go up to the back, please, and ready. Okay.
Hi there, Ben Grubb, Sydney Morning Herald. My question is, what does a realistic budget look like for Australia? I know it's a hard question to answer because we don't exactly know what any of the details are right now around an Australian space agency. Everyone I'm talking to is like, we can do this, we could do that, we could do that. So I want to know from Sarah specifically what you think or what you would like, and it's always more, but like what would you like in terms of a budget? And from Matthew, what do you think a realistic budget does look like?
So, well, I think the expert reference panel has some work to do yet to determine exactly what it is that we want our Australian Space Agency to do. I think some of the jobs of the Space Agency are reasonably straightforward and non-contentious. We want a front door for Australian international engagement. We want national coordination across the space activities that are happening, engagement with the really exciting new ecosystem of space startups that are starting to emerge in Australia. Beyond that, I think there's work and consultation for the panel to do to decide, what sort of space agency it is that Australia really needs in order to meet Australia's needs and not to mirror space agencies in other countries. not saying.
I'm the director of a centre of excellence that has about $40 million over 7 years, and I would hate to think that we would have to attempt space with that kind of money. So I would have thought you were thinking more about equivalent to a CSIRO division, tens of millions a year to be serious, but you also shouldn't put too much money in too early. I think you need to ramp up, otherwise you end up not being able to find enough people with the skills you need. So some sort of logical grading up. And it has to ultimately deliver sort of benefit for the taxpayer. So I think it's hard to come into the space race 50 years after we left it and think that you're going to be some dominant player. We have to pick very carefully niches and what's good for Australia and what we can actually do economically.
It is worth bearing in mind the UK Space Agency has a budget of about $450 million per year, but again, they make a massive return each and every dollar, or pound, I should say, that's spent. So it's seen as an investment. All right, there was a question up there at the back.
Just a question to...
So my question, so I'm with the South Australian Space School, but also with DST Group. My question for all of you is, in your facilities, what is the next big thing? If you could get that next discovery, what would it be for each of you?
Sorry, the facility or the next discovery?
Within their sphere, or their remit, I guess, what? Next new science, or next new discovery.
Within Astro 3D, we've got a couple of areas where I think the major discoveries are going to be made. One that you're probably going to talk about, Stephen. I'll let Stephen talk about one of them. That's where I think Australia is going to make a huge discovery in the coming years. The James Webb Space Telescope is just about to launch next year, and we have many Australian astronomers involved in this telescope. Fingers crossed that it all unfolds properly. If you've seen the launch videos, it's hair-raising, but if you haven't seen the launch videos, you should go online and have a look. This telescope aims to detect the first galaxies in the universe. We've never been able to see them before. If we can detect the first galaxies and then follow them up with our hyperspectral imaging, then we'll be able to understand what those galaxies were like, what their chemistry was like in the earliest days of the universe. I think that's going to be one of the other major discoveries.
Using low-frequency radio astronomy, so that means the MWA and then the SKA, in my view, one of the most incredible things that we're going to try and find is what we call the epoch of reionisation. So this is the period in the evolution of the universe from the Big Bang to the first billion years. So our universe is 13.8 billion years old. We can use these radio telescopes to effectively look back in time 12 billion years to watch the first stars and galaxies forming out of the hydrogen gas that was the product of the Big Bang. So those stars then evolved, the galaxies evolved, they formed us, they formed everything that we can ever experience. So we're looking back in time to really try and discover how the first steps to us came about. So that, I think, is one of the fundamental things that the SKA is aiming for.
So in my field, I will point to the other one of those space telescopes there, TESS, which will also launch early next year. It will be delivering thousands of new exoplanet detections across the southern sky in its first year of operation. And my team at UNSW is gearing up to commission a new instrument on the Anglo-Australian telescope early next year in order to follow up as many of those new exoplanets as possible, hopefully to find an Earth-like planet in a habitable zone orbit around a nearby star and be able to actually measure its density so that we can find out whether it really is rocky. Down the track, JWST will then be able to look at those things and actually try and probe what their atmospheres might look like if they have an atmosphere, and that will be incredibly exciting. The first attempts to actually look at what the atmospheres of a small planet look like and tell us whether the environments that we see here on Earth is common or incredibly rare.
So one of the areas that our telescopes are involved in at the moment, and that's very exciting, is that of fast radio bursts. So fast radio bursts are extremely bright, and extremely bright bursts that last very short periods of time and come from outside our galaxy. The first fast radio burst was discovered with the Parkes telescope, but our ASCAP telescope in Western Australia and the Utmost telescope, which Matthew is working on, are discovering more and more fast radio bursts all the time. The thing with FRBs is that nobody really has an agreed mechanism for what makes them happen, what could make such a massive burst of energy in such a short period of time. So over the next few years, we are going to have detected probably a couple of hundred FRBs, and that will give us a much better insight into what it is that makes them happen.
Just 2 years ago, the first gravitational waves were discovered from a pair of massive black holes that merged about 1 billion light years away. It would be really fun to catch a black hole destroying a neutron star or 2 neutron stars merging, and then we could learn about what makes up neutron stars. So that would be my best thing that could happen.
I might also chip in on this. I absolutely adore all of those potential discoveries, that they all resonate with me. In addition, I would say trying to pin down the nature of dark matter. And that's actually going to probably use almost all of the facilities we mentioned and supercomputer simulations on top and direct detection experiments here on Earth, like the Stoll Underground Physics Laboratory SABRE experiment. So yeah, there's a lot to look forward to here in Australia. Was there a question in the corner?
Yeah,
oh, sorry, we'll just, this younger gentleman just here. Yep.
So this is a question for Matthew. I was wondering, with the discovery of gravitational waves, do you think that in, say, the next 100 or 200 years, there may be practical applications in engineering for gravitational waves? Because obviously now there's not really much practicality use of gravitational waves, such as what was thought 100 years ago of Albert Einstein's theory of general relativity, but now it's used in every day with GPS systems. So, yeah, that's my question, I guess. Do you see any real commercialization use of gravitational waves in the coming centuries?
No. But I do think the technology that we have to develop in order to detect the gravitational waves will certainly flow out to industry. And we have examples of flying like mini gravitational wave detectors. Even though they're not detecting gravity waves, they're detecting gravity. You know, flying in aeroplanes, the suspensions that keep them very stable, the same ones that are used in LIGO are being used in industry already. When radio waves were first discovered, there was thought that there would be no practical application of them. But in order to generate a gravitational wave that you've got a hope of detecting, the kind of masses you need to move around are just stupefying, and it's very hard to foresee any technology that could do that. Even 2 neutron stars or 2 black holes coalescing make a mirror move by 1/10,000th of the width of a proton at a distance of 4 kilometers. These are like really tiny things. That's the equivalent of the width of a human hair at Alpha Centauri. These are like mind-bogglingly small things, and it's very difficult to see that we'll be carrying gravitational wave detectors around in our pockets.
I had hopes for the iPhone X, but yes, and if we could bring the microphone then down to the small gentleman here at the front. Thanks.
Yeah, I'm curious about what skill shortages that you are experiencing now and what skill shortages you anticipate in the coming decades, whether it's data science or whether it's physics.
Well, all of the above. I think all of the typical disciplines that you mentioned, physics, mathematics, computing, etc. Yes, we are deficient now, but what I see as really an absolutely critical skill set is the multidisciplinary skill set. And also people who have an understanding of both industry and academia. So the most valuable people in my team are people who've done a PhD in astrophysics, undergraduate degree in physics and maths, PhD in astrophysics, gone and worked in industry for a decade writing software, and then come back to academia. So people who've lived in different environments and bring a level of professionalism in some of these areas, as well as the extraordinarily good theoretical underpinning, coupled with the real-world skills and professionalism, I think it's a critical asset in our world of building things like this because you need people who are both broad and deep, people who are real system thinkers. And yeah, our system doesn't really encourage that. In fact, it's getting involved in projects like this that really drives the demand for that type of people. And so this is one of the ends of being part of mega science international projects, is that you then have a framework that people like that can develop and grow and then flourish in other areas. But yeah, absolutely multidiscipline for me.
Sarah?
Yeah, so I support all that from Steve completely. From our point of view, some of the people who come up with the most innovative and the best ideas for our instruments are people who can work on both sides of the science and the instrument divide. So people with expertise both in the engineering of the instruments and in the science and the astronomy that comes out of them. And that's an extremely difficult skill set to get from people. And that's certainly when we come across people who are really good on both sides of that divide, that's really great.
In Astro 3D, what we're really after is people who can combine theory and observations. So in order to understand how we got here across 12 billion years and to analyse hundreds of thousands of data cubes, we actually need deep theoretical simulations which can reproduce these data cubes. And in the past, what's happened is theorists have worked together in silos in different institutions around the world, and then the observers have also worked separately in silos around the world. And what we really need to do to be able to understand and answer the biggest questions that we have in astrophysics is to combine the theorists and the observers. It doesn't happen very naturally, but there are people who work with both theory and observations, and they really facilitate this transfer of information from understanding the observations, how we can get the theory to help us understand the observations and make future predictions, which can then be tested by future observations.
I would just follow up that examples like the square kilometre array really drive that sector-wide change, right? We are forced to work together, observers and theorists, because the scale of the facility and the problem, the challenge that we're trying to solve is just so vast. One thing that we perhaps do need to see more of is ways to facilitate commercialisation on outcomes, and that's something very front of mind for all of our panel here, and indeed in the SK office. There was a question, yes, at the front, and we've got a few minutes left, so.
It's a little bit of a three-part question, but it's about the GMT. I was wondering how it's funded, when it's going to be up and running, and what kind of results we can expect from it when it is up and running.
So the GMT is a partnership between a group of US universities and Australia and Korea. It is currently something like 2/3 funded by those partners, with extra partners currently being sought. We expect that it will have first light in its first form probably sometime around 2024, 2025. And I've forgotten now, as in all three-part questions, what the third part was. Oh, what's it going to do? It's going to do a whole load of amazing stuff. Because it's a really big, it's a $1 billion facility. It's not designed to do just one experiment. It's designed to have a working lifetime of 50 years. It's designed to have a suite of instruments on it that enable a broad range of science. So in my own field, it will have a very high precision spectrograph for basically measuring the speed of nearby stars as they go backwards and forwards in order to see or detect the presence of planets going around them. In other fields, it will have facilities for doing very, very high-resolution imaging, because it's so big, 25 metres across, 3 times bigger in diameter than the largest current telescope. If you use laser adaptive optics, the way Lisa described before, you get tiny, tiny little images, and so you're able to do imaging at scales that have not previously been accessible, that will be still many, many times higher in resolution than you get from space with something like JWST. So it will enable heaps of science of the stars of our galaxy, other galaxies, looking at the very earliest things that basically emit visible and infrared light back in the beginning of the universe. I expect it to make lots of discoveries, and the one thing that I can confidently predict is that anything I tell you now will not be the most important discovery it makes, because it's invariably the case that if you build a giant telescope, you try to predict what it will do in advance, and what you find is that the first exciting thing it does was one of the things you didn't think of.
So with the GMT and the SKA in the next decade, the world is going to make a leap in telescope size from about, in the optical, 8 to 10 metres to 20 to 30 metres, and in the radio from, a few kilometres to entire, square kilometre. I got it wrong, Sarah, but I'm used to doing VLBI, where you combine many telescopes together. And when we make these great leaps in size, always that's when the major discoveries have been made. So the last time the great leap was made was about, it was about 20 years ago, 20, 30 years ago. We went from 2 to 4 metre telescopes up to 8 to 10 metre telescopes. And in that time period, just because of that leap in technology, we made major discoveries. For example, the discovery of many extrasolar planets around nearby stars, understanding the supermassive black hole and the gas surrounding it in our own galaxy, and also the discovery that the universe is accelerating was enabled by these sorts of leaps in telescope size. So there's going to be similar major breakthroughs in our understanding of the universe allowed by this leap in telescope size that's about to happen.
So it's never been a more exciting time to get into science. This will have to be the final question. We'll try to keep to time.
Yes, thank you. Paul Curnow from the Adelaide Planetarium. My question is directed to Stephen. Stephen, could you comment on your work with the Yamatji-Warraji people and the uniting of cultural astronomy with modern contemporary astronomy?
Yeah, we don't have enough time to do it justice, but in summary form, over the last decade, more or less, I've been working closely with Indigenous people from the part of Western Australia in which we are building these radio telescopes, and it's the traditional land of the Wajidi Yamatji. So back in 2009 was the International Year of Astronomy, and we started the project back then, and the idea was to get Indigenous and non-Indigenous people together, specifically scientists, to talk about our different views of the night sky and the universe and the stories that come with that. We did several field trips out to the site in the middle of the Murchison Shire. We built campfires, we sat around, we looked at the stars, we traded stories. From that point, the Indigenous artists put together a massive exhibition of the paintings inspired by their traditional stories and some of the experiences talking with the scientists. That exhibition has travelled the world several times, has been sold out several times, and in fact I think Jerry told me that part of the exhibition is here this week, South Australia Museum, and when's it on? From now to February. So if you want to see some extraordinary Indigenous artwork inspired by astronomy, get along and see it if you've got the chance.
That is fantastic. I think that is us out of time. Is that right, Jerry? Oh, all right. So look, if you have any more questions, please do come up and speak to our panel throughout today and tomorrow if you see us hanging around. With that, I would like to thank the Australian Government's Square Kilometre Array Office for bringing together this amazing group of thinkers and doers. And it could, oh, we're getting an extra 10 minutes because the other ones overran. Sweet. All right. Looks like time can expand as well as space. All right. If we bring the roving microphones out. 5 minutes. All right. Okay. I heard 10.
Any advance on 5?
Yeah, we're haggling. Yep.
I'm interested in what's going to happen to secondary schools now that there's been the announcement of the Australian Space Agency, and what you're looking for in secondary students and how we can prompt and provoke those secondary students to move into the fields of science. I know myself, I was always interested in science, and when I actually got into high school, it took a while to sort of connect maths and physics to the science. My teachers at the time weren't very good at doing that. They were saying that science was, you know, especially space was probably something that we wouldn't do in Australia. So now this has possibly changed. So I'm very curious to know how we're going to change that.
I might quickly jump in at the start, actually. I would say that one of the amazing things about space science is that it is multidisciplinary. It appeals to a variety of interests in that regard, but it's also, in the sense of gender diversity, we find pretty much even male-female enrollments in programs such as we do at Swinburne with the Haileybury College, where we are sending an experiment up to the space station. We've had equal gender representation, which has been fantastic. Something that appeals, I think, about the exploration of space to everyone. Sarah, do you want to follow on that?
Yeah, so I agree certainly that the establishment of Australian Space Agency will be great for encouraging secondary students and primary students and university students indeed to stay in science, engineering, maths. We have a programme for secondary students called Pulse at Parkes, where we work with the schools, and the students can actually control the Parkes telescope and look for pulsars. And they, as you might imagine, find that very exciting. We've taken this indeed internationally. We've been to Japan and recently to South Africa, to our SKA partners in South Africa. And so I think that hands-on engagement, and CubeSats were mentioned earlier as another example, is really important in getting students to, completely understand that science and technology is for them. It is something that they can do.
Lisa?
In the Australian Astronomy Decadal Plan, it identified a great need amongst high school teachers for interaction directly with scientists. So it called for astronomers to engage more directly with the high school teachers to allow them to use astronomy as a tool for engaging students in science in general. And examples of this are, for example, we have a Telescopes in Schools program where astronomers take a telescope, give it to the school and teach the students and the teacher how to run the telescope and conduct science projects with the telescope. And this has had great success rates at allowing students to enter physics in the beginning. So more students enrolled in physics. In fact, it increased by 50% just to do this program. And then all of those students ended up doing physics or other areas of science at university, and they cited this program as the reason. So this is the sort of thing that we as astronomers are increasing ever more with time, in active engagement with individual teachers and schools across the country. Some of these programs we're rolling out nationwide, and you've already heard from Sarah about their program as well, which is also highly successful.
Is there any other programs everyone wants to give a little plug for?
I'm not going to plug for a program, but I think Matthew hit the nail on the head a little bit. There has to be a career path through this sector. So astronomy is in a very fortunate position. It's one of the most attractive sciences. Everyone stood outside at night and wondered at the stars and where we come from. So in terms of our public outreach and educational outreach, we do incredibly well across all levels of the educational system. So it's really easy to get people hooked. But what's going to keep them in it is the prospect of a feasible career path through the system. So something that involves academia and industry. And I think that's the pathway for the future, is to have a system that enables people to take up those STEM subjects where they can move in and out of academia and industry over the course of their career. So I think the space agency concept could provide a real to generating that sort of framework. And it comes back to Matthew's point, career progression, career paths, persistence of effort, persistence of funding, having an organisation that's fit for purpose and will do the job that we want. And it's got to exist for a long time. So, once you create that, then you'll have a better prospect of kids and, let's face it, parents being willing to go down that path with their investment.
All right, well, now I think we really have run out of time. So, again... One more? Have you got a microphone?
Yes. Well, he does now.
Doesn't sound like it.
Oh, come on.
I was just wondering if you know how astronomy technology could be used for tackling environmental challenges on Earth?
Wonderful question. I suppose Lisa's already talked about some of the ways in which you can use the technologies for astronomy to understand atmospheric composition using laser guide star systems. I know one of the faculty members at our own university has indeed developed his own deployable system for measuring greenhouse gases using technologies that he developed through astronomy to basically make a small unit that you can stick it almost anywhere, and it looks up at the sky and tells you what the path of carbon dioxide is above you. The sorts of technologies that we use, the imaging technologies that we use in astronomy all the time, also underpin any sort of Earth-based imaging system. So if you want to understand land degradation, you use hyperspectral imaging of large tracts of the country in order to understand those sorts of things. Yep, very quickly.
So an example I'd like to give is our site in Western Australia that you can see there in the SKA picture. It is very remote, and we had to work out how we were going to power it. And so we have recently been rolling out the first hybrid solar power system that's been used for a astronomy site anywhere in the world, as far as we know. And in order to do this, we've got the biggest battery in Australia, and our partners, Energy Made Clean, have rolled that out. But for them, it was a really interesting technical challenge because our sites need to be really radio quiet. You need to make sure that none of the electronics or anything that you've got on site interferes with the telescope. So they've had to work with us to put a lot of shielding around that battery. And that's a whole new now area of technology that they can take to other customers and say, now you too can use a solar array with a radio quiet battery. And so we know that they've got interest, for example, from the defence field in that. And so that's expanding the use of photovoltaics and solar into new areas where it hadn't been able to be used before.
And I would say that's the biggest battery until old mate Elon rolls out his effort here in South Australia. So with that, could you please join me in thanking our fantastic panel of astronomers and also the Australian Government Square Kilometre Array Office for putting this on. Thank you so much.